Welcome again to this class, and so far we had been discussing mainly ordered systems, that is translationally ordered systems which are actually crystals. So in crystals what we have is we have a potential V of R is equal to V of R plus Rn, where Rn is equal to N1 times A plus N2 times B plus N3 times C, N1, N2, N3 integers, and A, B, C are primitive lattice translation vectors. But solids do not mean just crystals, they can also be disordered systems or amorphous solids. So today we will discuss something about the amorphous solids. So we can have amorphous solids which do not have translational invariance. Simple example of these solids can be obtained from a modified Kronig-Penney model. So if you are looking at a one-dimensional chain, you can actually model it as what is called a Kronig-Penney model. Which involves potential energy boxes which are periodically spaced on a chain, on a straight line. So for example, you can show this way. So in this, the distance between the boxes A is a constant, distance between neighboring boxes, and then the depth of the potential well, which is V naught, let us say, V naught is also a constant. Now when we go into disordered systems, we can think of two types of disorder. One is maintain the depth the same, depth and width of the potential box the same, identical, vary distance between boxes. And another way you can do it is maintain the distance between boxes the same, between neighboring boxes the same, identical, but vary the depth of the potentials in each box. These variations are done randomly. So, let me draw the pictures corresponding to this. So, one belongs to the following. I have identical boxes, okay. So, this distance is random nearest neighbor distances. So, then what happens is, supposing in each of these boxes the wave function, when they are isolated boxes, they are, let us say, phi y, phi I. So, this is phi 1, phi 2, phi 3, etc., where phi I is the eigenfunction of a particle in an isolated box. It could be in the ground state for convenience, independent box. So, then in that case what is happening is that the transfer integral or the Hamiltonian matrix integral T equal to h I comma I plus minus 1 is equal to phi I h phi I plus minus 1 is random, because the distance between the boxes are random. So, the overlap of the wave functions are random, and because of that you will have randomness in T. So, this is called off diagonal disorder. And is found, for example, in, say, in liquids like mercury or germanium at a fairly high temperature, etc. So, in this case what happens is that the wave function overlaps will be different. The system still continues to be conducting. The system does not localize the states. It only changes the bandwidth in some sense. So, it does not localize the states and will be conducting. For partly filled bands, or when each of these boxes is not completely filled, that is, every state in the box does not have 2 electrons, then in that case it is a partly filled box, and the band that ensues is the partly filled band, and that will be still be conducting. But what is interesting is another kind of disorder. So, the second kind of disorder is the following. I can illustrate that by the following. Etc., etc. Okay. So, in this case what happens is the potential well is having a depth which is V equal to V naught plus some random number psi. So, psi satisfies the condition minus W by 2 less than psi less than W by 2, where W V naught minus W by 2 is the shallowest potential energy box, and V naught plus W by 2 is the deepest box. Well, having said that, now, and psi is a random variable. Which takes a value between minus W by 2 and plus W by 2 randomly, and this can be distributed in any way you want, distributed for example uniformly, which means every value is actually having the same probability, every value of psi between minus W by 2 and plus W by 2 is the same, or Gaussian distribution, or it can be any distribution you can think of, any arbitrary distribution, not necessarily one of the named distributions. Now, in this what you are seeing is that the off diagonal matrix element phi h phi plus minus 1 is the same for all I. That means the transfer or the hopping integral between different sites is completely uniform, but what is not uniform is the diagonal matrix element phi h phi equal to epsilon I is randomly distributed. For this we can define a disorder strength the strength of disorder as delta is equal to W by B, where B is the bandwidth. And the bandwidth in one dimensional chain with nearest neighbor hopping is actually 4T, because the dispersion is 2T cos Ka, and so it will be 4T is the bandwidth in 1D nearest neighbor chain. Well, in this case we can have localized states simply for the following reason. For example, when you are looking at a this thing Kronig-Penney model, the uniform one, what happens in these is that you always have states which are, so here you see that you have a state here, a state here, a state here, a state here, state here. So this distance A is a constant between those. So now what happens is that because it is a finite potential well, then what you will see is the wave function is going to be leaking out, and because the energy levels in each of the boxes are identical, this is going to give me a quantum resonant tunneling. And it is this quantum resonant tunneling that is responsible for extended states and also for conductivity. Well, in our case here, we can have localized states if the disorder is weak, and extended states if the disorder is strong. Sorry, the other way around, localized states if the disorder is strong and extended states if the disorder is weak. Is exactly not the situation. I will talk about it a little more afterwards, but you can roughly say this is the case. Now, in this situation, what happens is that how do you decide if a state is extended or localized? How to decide if a state is extended or localized? For this, let us assume the following. Let the state be psi of k, which is actually a sum of all the local states with Cik as the coefficients. So, this is a linear combination of all the orbitals or the particle in a box states with coefficient Cik for the ith site eigen wave function. Okay, so in this case I can say that I can define what is called an inverse participation ratio I of k, which is equal to sigma over I Cik to the power 4 divided by sigma over I Cik squared the whole squared. So, Ik is called the inverse participation ratio. So, as you see from this, what you find is that if a state is fully localized, then I of k is equal to 1, because the denominator is just the normalization constant and Cik is equal to 1 for a specific I. So, I of k is equal to 1 and it is 0 for all the others. If a state is delocalized, is extended or delocalized, then I of k will depend on the size of the system and it goes as I of k goes as 1 upon L to the power some d, where d is related to dimensionality. Well, what happens in a 3-dimensional system in general is the following. That is, let me write down how the density of states, heuristic plot of density of states n of E versus E. So, you have something that goes like this in a true band which has full translational symmetry, then at the band edges the density of states goes to 0, but in a disordered system it is not necessary that it should go to 0. Now, in this case, if the disorder delta is small, then states in the edges of the band are localized. So, these are all localized for small delta. Well, why are the states in the middle extended? The states in the middle of the band are extended simply because how do you specify what a density of states? N of E, the definition is number of states per unit energy and per unit volume. So, if you take a small volume of the sample, in that we have more states in the middle of the band than towards the edges. So, what it means is that the states in the middle can overlap more easily, because there are more states, and so you can have wave function of one state can actually extend into the wave function of another state, and so they can overlap, unlike states in the edges, because in the edges you have fewer states. So, to overlap these states within a particular volume is more difficult, and so you will see that the entire localization starts occurring from one end. Now, if delta is greater than delta C, some critical value, then what happens is the system is fully localized. All the states are localized. So, and this happens, the system becomes an insulator. Now, when I go back and look at the other picture for intermediate or small delta C, what I am looking at is below a certain energy from the edge, which we call say EC1, from the lower edge ECL, or let me just call it EL. EL and EM, the max, the lower one and the higher one, you see that all the states below the energy EL or above the energy EM are all localized. So, if I have a filling in this system, which is the filling fraction is such that electrons are filled only up to this, then the system will be insulating. So, this will correspond to insulating region. But on the other hand, if the filling extends beyond that, beyond EL or EM, then what happens is, so it goes up to this, then here I should not have this is a higher energy, so it will not, they will not be occupied. Okay. So, if I am looking at this one will be metallic. So, EL is called the mobility edge. Below EL, all the electrons are localized, and if the electrons are filled in the band beyond EL, the system becomes conducting. So, you will have a transition from, as delta is increased, for say a half fill band, the system goes from being an insulator to a metal. Being a, rather, as since we are increasing delta, it must be going from a metal to an insulator. So, this is a disorder driven metal insulator transition. Well, how does the transport occur in disordered systems? For that to occur, the first thing that we need is the wave functions should have non-zero overlap. The wave functions should have non-zero overlap, and 2, the energy between the states must be comparable for conduction at reasonable temperatures. So, what we are saying is that, so this means that the hopping is not necessarily to the nearest neighbor. The hopping of an electron is not necessarily to the nearest neighbor. And the range the electron hops is variable. Depending on 1 and 2. Okay, so this process is called variable range hopping. This is called variable range hopping. The probability for variable range hopping P of r therefore is equal to some P naught times an exponential function of minus 2 alpha r minus delta E of r divided by k by t. This is because the wave function decays exponentially as e to the minus alpha r, and because two functions have to overlap, then it is exponential minus 2 alpha r. So, one is decaying as e to the minus alpha r, the other one is also decaying as e to the minus alpha r, and so that is what happens. And delta E of r is the energy range in the sample in a radius r where r is the distance of hop. So, what we are saying here is that the electron is going to hop a distance r, let us assume. Then what is the energy change that you will be having over this distance r, you can estimate, and that is minus delta E of r, and kBT of course is the temperature at which you are actually doing the experiment. Now Mott obtained an expression for P of r, and consequently sigma at a given temperature T as equal to sigma naught times exponential minus T naught by T to the power 1/4. So, this is called Mott's T to the power 1/4 law, and it is actually quite easy to derive this expression, which I will do it in the next lecture. And for now I will stop here, and we will again meet for the lecture to continue from here. Thank you very much.